Good morning. Today we're going to discuss the matrix method in optics. So far we have been looking at lenses and other optical elements using ray diagrams. Now the matrix method helps us analyze the same things from an analytical geometry point of view. So while doing matrix method or the ray tracing techniques that we used in the previous chapters, we are mainly considering paraxial rays. So we are considering paraxial rays, meaning only the rays that are close to the optical axis. Rays close to the optical axis. We are not considering rays that are not close to the optical axis. Or in other words, if you have, say, some lens in the path of light, any ray of light that is incident on the lens is only making a small angle, is only making an angle that helps us, that is for which this approximation sine theta is almost equal to theta is valid. So we are still going to stick to this paraxial approximation, and now instead of tracing the rays, we'll develop a matrix method. So to that end, first what we will do is we will develop a matrix for looking at the effect of translation. Then we will look at developing the matrix for refraction, and then we will see how we can use these two to, for example, look at a simple optical system like a lens. Okay, so now let's get to the effect of translation. Before we go there, when I say the matrix method, what I mean to say is, suppose you have some optical elements in a black box. You don't know what optical elements are in here. There could be several lenses, there could be some slits, there could be all sorts of inhomogeneous media or anything. This is just a box containing different optical elements. Now, if you know at this point, if you know the coordinates of your um, point from which light is going, so you can write this as xy, right? And I can represent this optical system based on whatever is in it. How many lenses are there, how many mirrors are there, so on and so forth. Based on all those things, I can come up with a 4 by 4 2 by 2 matrix, right? And this 2 by 2 matrix, when I operate it on the initial coordinates xy, I will get where my light from this point will end up at x prime y prime, right? So to make it completely very simple and straightforward, instead of drawing rays. So to do this, first let's consider the example of light going onto a convex lens or a biconvex lens. Now if I have a lens here, right, and we can draw the axis through the center, we're going to call this as the z-axis. Now let's consider a ray of light that is going like that, starting from this point, and it's going towards the lens, right? So now if I let me change the color of the ink. So now uh, let's say this starts at a height of, say x1, okay, and let's say at this point you are at a height of x2, let's say. Okay, now I can draw a horizontal here, right, and call this angle, right, as alpha 1. Similarly, I can draw another horizontal here and call this angle alpha 2. Okay, so now we are going to define a new quantity, right? We're going to indicate it by lambda. We're going to define this new quantity lambda as the refractive index n times cosine of the angle, or sorry, sine of the angle sine of alpha 1. So for example, at this point, for point 1 here, I can define lambda 1 as n sine alpha 1. Well, we will see where we'll use this, but I can also write this n sine alpha 1 as if I were to draw a vertical here, right? Then this angle, let's call it psi, right? So then psi would be 90 minus alpha 1, or let me call it psi 1, for example. Psi 1 would be 90 minus alpha 1. So I can also write lambda 1 as n cosine psi 1, right? And it's more traditional to use the cosines than sines, because what we are looking at is um, this angle here, psi 1, from the vertical, and this position x1 here. So if I have x1, I know where my ray is, and if I know the angle, I know which direction it is going in. So if I know lambda and x for at any given point, I can with the set of lambdas and x's, I can retrace the line. If I have the coordinates lambda and x, I can retrace the line. For example, if I give you that this lambda 1 x1 after some time is at a position x2, at a height of x2, making an angle of 2 degrees, then you can draw a straight line between lambda 1 x1 and lambda 2 x2, and you know which way the light is going. So this new quantity lambda has a name. It's called the optical direction cosine. So we're going to use the optical direction cosine to look at the matrix way of solving things. So now our goal is to develop a matrix such that given lambda 1 x1, I know my ray of light is starting from x1, and given lambda 1, I know at which angle it is going at. So this is my initial state, right? And what I would like to do is I would like to come up with a matrix so that I can operate that matrix on lambda 1 x1 to get the coordinates at another point, say lambda 2 x2, right? So my goal is to derive this lambda 2 x2 given the initial lambda 1 x1. This is the initial state, right? And this is the final state, right? So I want to develop some matrix here so that when I multiply this lambda 1 x1 with that matrix, I get lambda 2 x2, right? So now let's look at the case of translation and develop this matrix for translation here. So for in case of translation, we are going to consider that this entire medium before the lens is made up of the same refractive index, that it is a homogeneous medium, right? So if it is a homogeneous medium, then there is no reflection or refraction, because before the ray of light hits the lens, we're only looking at the translation. So it is going from point 1 to point 2, only translation, right? If it's only translation, because light goes in a straight line in a homogeneous medium, the angle alpha 1 here and the angle alpha 2 there should be the same, because light goes in a straight line, and it doesn't bend or refract if it's in the same medium. There is no change in refractive index within that medium. So alpha 1 would be equal to alpha 2, right? So now if I call this distance between x1 and x2 as d, right? If I call that distance between x1 and x2 as d, then you can see that I can write x2, right? So this whole thing is x2 here, right? And this part is x1, right? So I can write x2, which is the height here, this entire height, minus x1, right? I can write x2 minus x1, that is the difference between, that is this little tiny portion here. X2 minus x1 would be this tiny portion here. So that is the opposite side of alpha 1, right? That's the opposite side of alpha 1. So if I put opposite side by adjacent side, that gives me a tan. So I would have x2 minus x1 as that is the opposite side divided by d is equal to tan of alpha 1. Okay, so then I can write x2 as x1 plus d times tan alpha 1. Right? Convince yourselves that x2 minus x1, here the height is x2. If I knock off x1, which is this bottom portion, if I knock that off, I have x2 minus x1 left here, which is the opposite side for alpha 1, and the adjacent side is d, that is the distance between x1 and x2. So then we have derived a relationship, x2 is equal to x1 plus d times tan alpha 1, right? But like I said, we are only going to consider paraxial rays, that is rays that make very small angles, so that then we can make this approximation of tan alpha 1 almost equal to alpha 1. If I make that approximation, then x2 is equal to x1 plus d alpha 1, right? Now we also know that alpha 1 is equal to alpha 2 because we are only considering translation within the same medium. So if you are in the same medium where there is no change in refractive index, then the light is neither going to get, it's only going to get translated. It is not going to get refracted, which means the angle it makes with the horizontal is not going to change. And that's why we have alpha 1 is equal to alpha 2. And we defined this optical direction cosine lambda 1. So if I were to write lambda 1, that would be n times alpha 1, lambda 2 would be n times alpha 2, but because alpha 1 is equal to alpha 2, lambda 1 should be equal to lambda 2. Then I can write lambda